In this video I will explain how the maximum likelihood estimation principle can be applied to estimate a logistic regression model. Our data are girls and the dependent variable is whether a girl has had a menarche or not, and the independent variable is age. And we're fitting the logistic curve. So we can see here that when the girl's age is close to 10, which is the minimum in the sample, the predicted probability of menarche is about 0. And when the girl is 18, which is about the maximum of the sample, the predicted probability of menarche is about 1. And we want to estimate this logistic curve, how it goes, and it tells us the relationship between age and menarche. We apply the probability calculations to values that are ones and zeros. That's the dependent variable. And to do that, we use the Bernoulli distribution. The idea of a Bernoulli distribution is that we only have ones and zeros, and in this example the zeros are twice as prevalent as ones, and the population is always very large in maximum likelihood estimation, because when we take a sample of 1, 0 or 1 away from the population, the ratio of ones or zeros should stay the same even if we take a sample away from the population. The probability of getting 0 is 67% from this sample, and the probability of getting 1 is 33%. So when we have this set of observed values that are sample, we have 7 zeros and 2 ones. They happen to be in this order by random. It doesn't have any significance or any meaning, and we calculate the probabilities. Then we calculate the total probability by multiplying all these individual probabilities together. So when we know what the population is, then we know the probabilities of getting particular values from that population. In maximum likelihood estimation, the population is not known, but we have to estimate what is the effect of age on menarche in the population and what's the base level. And so we don't talk about probabilities, we talk about likelihoods. So the idea of maximum likelihood estimation is that we try to find a population that has the maximum likelihood of having produced these values here. So we don't know what the mean is or what's the ratio of ones and zeros. We only know the data, and we assume that the model exists for the population. Then we calculate, we have some guesses for this ratio, and then we calculate likelihoods. We'll calculate the cumulative likelihood, and we maximize the cumulative likelihood to find the maximum likelihood estimation by changing our model parameters. So for example, we could guess that the ratio is 2 to 7. That gives us probabilities of 78% and 22% for zeros and ones. We calculate the cumulative probabilities, and or we multiply everything together, and this is the likelihood of the sample given our estimated population. The maximum likelihood estimate is simply found by changing our guess of the ratio of ones and zeros so that this value here becomes as large as possible. This principle is applied to the logistic regression analysis. The idea is that we calculate using this logistic curve and this age here and the known ages and the known menarche status of these girls. We calculate the individual likelihoods for the observations, and then we use those individual likelihoods to find the best possible logistic curve for the data. How it works in practice is that we have some kind of guess. So we guess that menarche is a linear function of age and an intercept transformed using the logistic function. So let's say that the intercept is -20 and the effect of age is 1.54. We apply logistic function to the linear prediction, and then we calculate. That gives us the expected probabilities. Then we check how likely that particular observation is given the fitted probability. So for example, the first girl here is 13.6 years and she has had menarche. The linear prediction for that girl using this equation here is 0.94. Then the fitted probability using the logistic function to this linear prediction is 73.6%. So If the probability is 73.6% and the girl has had menarche, then likelihood for that observation is 73.6. Then we move on to the next girl, so that's 11.4 years and she has not had menarche. The linear prediction is minus 2.44, so it's calculated using this equation here. And we apply logit function, gives us 8% predicted probability. Because it's only 8% probable that this girl would have had menarche given her age, and she didn't, then the likelihood for this observation is 1 minus 8%, which is 92% here. We do that calculation, we calculate the likelihood for all the girls, and that gives us the product 6.4%. For computational reasons, we don't typically work with these raw likelihoods and multiply them together. Instead, we work with logarithms. So we calculate the logarithm of the likelihood, called the log likelihood for each individual observation, and we take a sum of these log likelihoods, and that gives us the full log likelihood of the sample. And we adjust the values of intercept and values of age, or the coefficient for age, to make this full sample log likelihood as large as possible. In practice, this is almost always a negative number, so we try to make it closer to zero or a smaller negative number.